All right. Hello. In this video, I wanted to review what we went over in class today and just put this out there so you have something you can look back on. In addition to this presentation, obviously on Canvas, hopefully this explanation will help you out in learning the statistical aspects of psychology. The good news is this is the fourth day of our semester, and we're going to use these tools throughout the semester a lot. So just by practice over and over working with these things, they're going to make a lot of sense by the time we get to April and definitely May. They should make a lot of sense for you. There's two main kinds of statistics we deal with up here. As you can see, we have descriptive statistics, which, as it says, they describe. The main aspect here is measures of central tendency, just trying to find out what the overall average is for a data set. And depending on the type of data set that we see, that'll determine which of these three versions of central tendency or average is most appropriate. Again, the mean is your standard mathematical average. You add up all the values and divide by the number of values you have. So if you have 5 people in your sample and their scores are 2, 4, 6, 8, and 10, well, you add those 5 numbers up. So 2 and 4 is 6, plus another 6 is 12, plus 8 is 20, and 10 is 30. You divide that by the number of values you had. That was 5 different scores. So 30 divided by 5 is 6. 6 would be our mean. Median is done in a little bit different way. Again, if we have 2, 4, 6, 8, and 10, you cancel out the highest and the lowest numbers. So cancel out the 2 and the 10. You then cancel out the next lowest and highest numbers, or highest and lowest, however you want to think of it. Cancel out the 4 and the 8, and you're left with the number in the middle, which again in this case is a 6, but it may not necessarily be the same as your mean. Finally, the mode. That's the number that occurs most frequently. In this sample I gave you, 2, 4, 6, 8, and 10, you don't have anything that occurs more frequently than another, but typically in a data set, you will have something done twice. We also have things that help us with variance, or how spread out data is, and we'll see that as we go. Again, range is taking your highest number minus your lowest value, highest value minus lowest value. And again, the tighter your range is, the less your standard deviation is going to be. The higher your range is, the higher your standard deviation is going to be. Standard deviation is incredibly important. It's complicated and kind of annoying to calculate, but it's very important to understand what it does. If you can't calculate standard deviation, if you don't remember the formula, it's probably not the end of the world for you. That question probably won't be in the final exam. They're probably not going to ask you to go through the math of squaring multiple data numbers, entries, and then then summing those up, dividing by the number of entries, and then square rooting the whole thing. That's probably not going to happen. But knowing how to use standard deviation, very important there. So we will see that in a moment. Frequency distribution, again, we will see examples of each of these, and each of these has a different appropriate measure of central tendency. Again, mean, median, mode are all the same for normal frequency distribution. Bi-modal should use the mode. And then if it's positive or negative skewed, anything that has skew to it, we want to use the median. And we'll show you why here in just a moment. Correlation coefficients we didn't talk about today in class. They are very important. We'll see that more next week. They will, especially for scatter plots, which we'll see on our sleep analysis and our stress analysis. Finally, we have inferential statistics, which is the part we really didn't get to today. It's, again, kind of like standard deviation. There's formulas. They're annoying. They're a little scary looking, but it's a very simple idea. You do a t-test in order to get a p-value. So the p-value is a result of a t-test. What a p-value gives you is the chance of error. The p-value tells you what % chance there was that the results of your statistics are due to pure chance. So if you take 100% and you have a 5% chance that your results are due to just dumb luck, there's a 95% chance that your results are due to what you were studying. And we consider that statistically significant. So if your p-value is 5% or less, you can be at least 95% confident that your results are statistically significant. That's the main thing we missed today. So if you get that, you could probably just shut the video off right now. If not, I'm going to keep going through the rest of it. We got about 50 slides to get through, so I'm going to go kind of quick, but I'll slow down when I need to. So again, central tendency, as it says right there, a measure of the tendency of scores to congregate around some middle variable. Again, we'll see some examples. Mode, if you have a number that comes up over and over and over, it's probably your mode. If something else happens more often, then that's your mode. And again, the mode is appropriate with bi-modal distribution. When you have two bumps, there has to be a valley between them, though. Mean, again, the mathematical or arithmetic average, again, add them up, divide by the number. And the median is the one that is in the middle based on the values, not halfway of the range, but the one in between the values. Okay, again, here are three of the ways we see it. Bi-modal is not represented here, but we have a negative skew. And think about what we call this one result way over here. What was that called? That's an outlier. So if you have a negative outlier, that's going to really pull your mean the most. So if you have everything's grouped around having like a 70 over here, that's your mode. In normal distribution, it's your mean, median, and mode. They're all the same. But then one person comes in and gets just a 0. They don't do anything. They get a 0. That's going to really kill the mathematical average, the mean. The median's only going to move by one place. It's going to move by one data set over. So it may not move at all. The mode definitely will not change because whatever that number was, say it was a 70 was the score, it's still the number that the most people got. If you had 9 people in the class get a 70 on a test, one person gets a 0, well, you still have 9 people getting 70s. The median, it may not move. It could, but it may not, depending on how many numbers are in the mode. Again, normal distribution, half the people are below, half the people are above. The most people are right there, dead center. And then finally, positive skew is the same. You have an outlier on the high side of things. Mode doesn't change. Mean changes a lot. The median, as we said in class, it's your Goldilocks. It's one that changes a little bit, or I guess what Goldilocks is looking for in the bears. I got to work on my fairy tale knowledge. And there you see you get an outlier. So we have what looks like roughly normal distribution here, and then that one outlier really outperformed. So we have positive skew. The outlier is above the average. It's a positive skew. If it's below, negative. And there you see that. Outlier, negative skewed. Outlier, positive skewed. All right. Here again, we have an outlier. This is a very extreme outlier. We actually have something of a bi-modal based on this look, or almost trimodal, but really we won't get too concerned with that. If you have an outlier, it's positively skewed, and that's it. Whether there is bi-modal or not with an outlier. So we got all these people grouped in here between 15 and 50, and then a couple of cats are way, way out there, just like Warren Buffett or crazy Bill Gates rich. So that's going to pull the mean the most. The mode doesn't change, and then we're going to use the median when we have a skewed distribution. There's your bimodal. So again, in this case here, I think in the example used in class was the number of cups of coffee drank by the entire population of Chase High School. So students and faculty. And odds are, us faculty, we're older, we need a little more energy help, so maybe we drink more coffee. Now, if you're talking about energy drinks, maybe the students are this group where they're drinking, 40 energy drinks a month, and the faculty drink 30. But you're going to have, overall, you're going to have two humps. You have to have the valley in between. And again, mode is the way to go with bimodal distribution. All right, let's move on. All right, so again, I'll skip that example. I don't like it. Don't like that one. Here we go. There's the one we saw in class, which actually turns out is not a very good data set because we're dealing with a lot of percentages and whatnot, or not percentages, decimals. But here you see we had all our test scores. We can add them up. I think most of you got that 787 as you add them up. There's 10 numbers total, so we get 78.7 is our mean. And that could be right if this is normal distribution. It is right, but it could be the best choice. The median, you have to put the numbers in order. Don't mess that up. Put them in order, or I would mess up. And then just start checking them off. It's not 37 or 91. It's not 72 or 91. Not 74 or 88. We keep working away, and we end up being right between these two. If you don't land on one number, you just find the mean of those two numbers. Add them up, divide by 2, you got 85.5. And then finally, the mode was 88. And if this was bimodal, that would matter. Now, again, be careful. I mentioned this. This is our mode, the 88. We do have 91 that also has multiple entries, but there's no valley in between. So that's just part of either normal or most likely a negatively skewed data set. If that they're still together, there's no drop between them. If you had like a 90 right there, an 89, maybe it's bimodal. But the fact that it's nothing between those two, it's not bimodal. So again, I would say in this example, with it being skewed, median should be the best. All right, we already mentioned range, the difference between the highest and the lowest, and then we'll talk about standard deviation. So in this data set, 9 minus 3 equals 6. There you go. Standard deviation, very important. Again, how tightly grouped is our stuff? That's actually not the reason it's important. We'll get into that in a second. It's important because it helps us with our inferential statistics and our percentiles. Here is a much more convenient data set. Let's see if we can go full screen here, make it a little bigger for you. So we have these scores. Again, this could easily be Unit 1 test scores, okay? Very realistic. And in this example here, we have the total sum is 640. There's 8 students in this fictional example. So the mean score is an 80. Nobody actually scored a mean score of 80, but that is our mean. Then what we're going to do to find standard deviation, the first step is to find out how far each number is from the mean. The positive and the negative here, it does not matter at all because we're about to square this. Anytime you square a number, it has to be positive. So 2 negatives times each other, positive. 2 positives is a positive. So 8 times 8 is 64, 6 times 6, 36, obviously going all the way through. And then what we're going to total is the squared of each individual deviation. So we total these up, sum those, and that's your 204. This little phrase here, sum of deviations squared, has messed me up before. I've tried to sum this and then square that answer, and that will not work out. You have to square them first and then add them together. Once you've done that, you can divide by the number of scores. So 204 divided by 8 equals probably 25, it looks like. And then you take the square root of that 25 and you get a 5. Okay, here is a different data set. Okay, I was getting confused there, but it's just a different data set. So you have Class A and Class B. I should probably read the title of the charts. That would be a good idea. So we have, in this example here, the left example, all the scores are between, looks like a 72 to an 87. So the range on that would be 87 minus 72 is a 15. Not too big of a range. If we come over here and look at this set, we got a couple people that aced it. They got hundreds, and a couple people got 60s. So our range there, 100 minus 60 is 40. So just think in your head, which one's going to have before you even look at the bottom, what's going to have a larger standard deviation? Something with a range of 40 or something with a range of 15. And obviously you probably have looked here. The standard deviation on this one is 3 times higher, okay? Because the deviation for the means are a lot bigger. And when we square those, that's exponential growth there. So this one is 3 times bigger over here. Same exact math, but it's a 15.8 standard deviation. All right, this is a biggie. We finished class with this image today, and it's very, very critical to understand it. There's a couple of rules here. Let me include a couple text boxes for you real quick. I think they might pop up later, but I want to go ahead and put them in. So, first of all, in this case here, they're probably dealing with IQ. These numbers are very consistent with IQ. Now, the way IQ is measured is a person takes a test, and they're going to get a score that is going to give them, well, let's say 100 means you have 100% of what you should know, or the average person should know at your age, okay? You don't have to worry about anything more than IQ for that, at least not for a few more units. So if you score 100, that is the mean. That is the average. You've done exactly what you were supposed to do, all right? If you score better than that, good for you. Not whatever, doesn't matter. All look at statistics. So if you score the mean, you are dead on. It means your standard deviation is 0. Now, in this example, based on the variance in this in the whole population, you have. Sorry, I gotta send one text real quick. Sorry about that. All right, the variance or the standard deviation is 15 points. So, if you score within 15 points of 100, you are within one standard deviation above. If you score within 15 points below, you are within one standard deviation below. That's not so important. What's important are these percentages right here. These are consistent through any normal curve. I hope this is making sense. I'm going to clean it up here, I promise. All right. If you score dead on the mean, you will notice that there is just as many people below you as there are above you. So there's 50% of the population scored worse than you, less than 100 on an IQ test, and 50% of the population scored better than you on an IQ test, which means you are in the 50th percentile. When I'm saying that, it is not percentage, it's percentile. If you were dead on a 100 score here, which is our mean, 50th percentile. Gray font is not your friend. Okay. All right. So again, if you score 100, you are on the dead on mean, also the median and the mode. And you've scored better than 50% of the population, 50 percentile. You might have scored an 80% on the test. You got 80% questions right. Well, so did half the population. So you're 50th percentile. However, let's say you didn't score that. You scored 115 on the IQ test. Okay? I'm sorry. Is that right? Yeah, you scored a 115. That's the result that came back on the IQ test. All right? You are one standard deviation above or greater than the mean. If you are one standard deviation above, not only did you do better than all 50% of these people, you also did better than the 34.1% of the people that got between a 100 and a 115. So we add 34.1 to the 50% over here, and you did better than 84.1 or 84% of everybody else. You didn't get 84% right. You might have gotten 91 questions right. I don't know. Or you got a 115, which whatever that relates to. But you are in the 84th percentile is what they're saying. Okay? If you score better than that, say you score like a 120, you're somewhere sitting over here. We're not going to go into those kind of numbers. In AP Psychology, you're going to get numbers that lie on set standard deviations. So you won't see a 120 or a 123 here. So let's go through a couple more examples. You get a 130. Well, 130 is 30 points above the mean. 30 greater than the mean. Our standard deviation is only 15. So that equals 2 standard deviations above the mean. Hopefully you've seen the greater than character, the caret there from math. That just means more than. So your 130 is 30 more than the mean. And since the standard deviation is only 15, that is 2 standard deviations above the mean. Well, that you had 50. If you were at the mean, you were better than 50% of people. You're the 50th percentile. If you're one standard deviation above, we add 34%. You're at 84th percentile. And now we add another 13.6 to that. 84 plus 13 is 97. Plus the 0.6, the 0.1, you're at, what is that, 97.7? We'll just call that, it's either 97.7 or 98th percentile. You crushed it. You did better than 98% of the population. That's a lot of people to outdo. All right. Then finally, obviously, if you do better than, if you get a 145, you have crushed it. So you hear people say they got a 200 on their IQ score. They're probably full of crap. Because if you get a 145, that means that you are 45 points above the mean, which is 3 standard deviations above the mean. And therefore, you did better than, well, 99.9%. You're in the 99th percentile. So there might be one cat somewhere that beat you. This guy over here, but I wouldn't worry about that guy. He's probably off messing around at MIT or Harvard right now. So you crushed it. All right. So we've covered everything on the high side of the mean. Let's look at the low side now. All right. Maybe let's relate this to height. It's all IQ. We'll leave it alone. So let's say here you scored an 85. Okay. That means you were 15 points below the mean. All right. And which is 1 standard deviation. 1 full standard deviation below the mean. All right. So you can try to add these up. But these numbers get a little tricky over here. The easiest way for me to do that is 50 minus 34. 50 minus 34 is 16. So you are in the 16th percentile. Okay. You did better than 16% of the people. Also, that means that about 84% of the population performed better than you. Okay. Now, next one here, if you get a 70 on the IQ, that means you are now 30 points below the mean, which is 2 standard deviations below the mean, which means you did better than about 3% of the population. You're in about the 2nd percentile. None of you are in that. No chance. All right? So that's how standard deviation works. Now, we can change these numbers. The mean is not always going to be 100. If you're dealing with IQ in a normal population, it will be. And the standard deviation of IQ will generally be 15. That box is annoying. There we go. But this could be a lot of different things. Again, if we're talking about height, that mean number is probably going to be around like 5'10" or so. And that standard deviation, I'm not sure. It might be like 3 inches, but 2 inches. It doesn't really matter. Okay? But that's the general tools that we're going to use for that. All right? So again, you see it again there. The other thing we want to look at, and I drew this in there today, but let's look at a line here. Okay? If we were to look at just people that score within 1 standard deviation of the mean. We got ends on these lines. Yep, there we go. Nice fat lines. Good. Okay. There we go. All right. If the test asks you, and it probably will, all right, what percent of the population scored between an 85 and a 115? Now, it's not going to give you these numbers right here. That'd be too nice. You have to know them. So it might ask you, given that the mean of a normally distributed data set was 100, they told you it's normal, so you have to know these numbers. And they told you the mean was 100, and the standard deviation was 15. They're going to expect you to be able to calculate that 1 standard deviation below is 100 minus 15, which is 85. And then 1 standard deviation above is 100 plus 15, so it's 115. They will ask you what percentage of the population scored between an 85 and 115. What they're really asking you is what percentage of any normally distributed data set scores between 1 standard deviation of the mean. And it's always 34 plus 34, it always equals 68. Okay? So, scores within 1 standard deviation is always going to be 68%. If it's normally distributed, that's the key. Can I center this? I can. There we go. All right. Now, it's not always going to be 1 standard deviation. It could be something else. So let's just copy. How do I copy this? All right. Here we go. Now, what if they ask you what percentage of the population scores between two standard deviations of the mean, or between a 70 and a 130? Well, it's not going to be 68% anymore. Now we're all the way up to 95%. Let's double check that real quick. I'd hate to tell you the wrong thing. So, take out my calculator here, and we've got 13.6 plus 34.1 plus 34.1 plus 13.6 equals 95.4% of the population. So that rounds down to 95%. And we got one more time to go, don't we? We have what percentage of the population scores within 3 standard deviations of the mean. All we're really doing is taking that 95 and we're adding 4.2 to it. That's it. So if we take 95, well, it's really 95.4, and we add 4.2 to it. Well, 95 plus 4 is 99, and the 0.4 plus the 0.2 is about it should be 0.6, but it's really 0.7 or 0.8, something crazy high like that. So it's darn near everybody. So this number might be a little off there in the decimal. Just know 68, 95, 99, okay? Not quite 100. You can't say 100 because there will be people, those outliers, well, not exactly outliers, but your real extreme numbers on either side of any normal distribution. But 68, 95, 99, you should be in pretty good shape. All right. This is kind of a neat thing here. If you ever seen, was it The Price is Right? You know, I think it's Blinko board. You can watch this website. You can watch it all day long if you want. You can even speed it up so it'll go faster. But this is all randomized. If you had your own little marbles and pin board, you'll start to notice the way it's looking here and what kind of shape are we getting. It's not perfect, but the longer you let this go, the more this is going to begin to resemble normal distribution. Notice we've had none of them work all the way over here or all the way over here. Well, not yet. Eventually you will. Oh, starting to get very bell curve-like. I don't know about you. That's enough of that for me. Okay. So that could be something you could look at there. All right. So again, IQ follows a normal distribution. In this scenario, again, mean 100, standard deviation is 15. So there you go, 115 to that. Let's do a review. Think in your own head right now. If you score 100, what percentile are you in? You scored better than half the people, you're in the 50th percentile. If you scored 115, what percentile are you in? A 115 is right here. That is one full standard deviation above the mean. So not only did you better than the 50% of the people when you were at the mean, but you did better than another 34% of the people here, so you're in the 84th percentile. What if you score 130? You have a real great day. What percentage do we add in here? We already had 84. We're going to add these in. We're going to add in, I believe it's 13.6. So now we're up to about 90, what do we say that is? 97? 97.7 percentile, something right there, about 98th percentile you're talking about. And if you really crush it and you get up here, you're adding another 2.1. So now you're up to like 99.9. You did better than 0.1% of the population did better than you. So if you get a 145, you're really doing great. Same opposite, again, if you score an 85, what percentile are you in? Well, 50 minus 34, you're in the 16th percentile. If you score a 70, you're another standard deviation below, which is a 13.6 you take off, you're about the 2-3 percentile. Finally, what percentage of the population scores between an 85 to a 115? We're saying between one standard deviation below to one above. They're both 34, so you have 68% of the population scores somewhere in here. And if you look at this thing, by far the highest number of people are in this population, okay? So there we go. Moving on, okay? What percentage below? Oh, look, the same questions we just saw. 50% below, 50% above. All right. There's your normal distribution again. So what percentage of the population scores between an 85 and a 100? Now it's 34.1. And again, we keep reusing these numbers for one reason. It's because we're staying with these numbers. If these change, then these change too. However, the percentages do not change because it's normal distribution. All right? So there again, 68% in one standard deviation of the mean. At some point, we'll use examples that aren't always 115. Okay, 95% within 2 standard deviations. And only a very small, so if it's 95% are within 2 standard deviations, then what percentage are below 70 and what percentage is also above 130? So if this is 95, everything else must be 5%. It's probably like 2.4, but again, 5% sounds better. I'm sorry, 4.4. All right, so you are the 4th tallest person in a group of 20. It means you're taller than 80% of the population. There's 16 smaller. So you're in the 80th percentile. I scored a 100. It was the mean, some average, 50th percentile. Cool. You scored a 115. Again, 1 standard deviation above. You're in the 84th percentile. Or 85th, looks like. All right, we're almost done. Inferential statistics. This allows us to test the hypothesis. And again, as I mentioned at the very beginning of the video, we're going to find a new formula. It's going to tell us how to run a t-test, and the t-test gives us a p-value. That p-value, the higher it is, the worse it is. We want a low p-value because a p-value tells us how good of a chance there is that our results are due to pure chance. And we want chance gone. We want to make sure our information is statistically significant. All right. So again, they did as an experiment. We have a caffeine pill for an experimental group. And when they say a sugar pill, I know that sugar has caffeine, but in this example, it's supposed to be just nothing. Okay. Sugar pill is just a general name for a placebo. Okay. Something that does nothing. So caffeine pill is our experimental group. That's our independent variable. And then the reaction time would be our dependent variable. Good job. All right. So again, we've got the experimental group. They reacted on average in 500 milliseconds, which is about half a second, but at a standard deviation of about 172 milliseconds. So that means if you are in the experimental group and you reacted in 500 milliseconds, you're in the 50th percentile of that group. If you responded and say, what's 500 minus 172? 328 milliseconds, you are 1 standard deviation faster than the mean, which would put you in the 84th percentile or maybe 85th, okay? Either way, it's about the same thing, all right? If we're looking at the control group, their mean was slower. They were about 0.6 of a second, so 100 milliseconds slower, but their standard deviation was closer, a little bit tighter there, okay? Again, sugar pill or placebo, those are synonymous in experiments. So here we go. We have 2 different groups and time for a t-test. Was the caffeine actually what made them faster, or did the people that were a little bit twitchier that day, a little bit more sharp, just happen to be in that group? Okay, we'll find out. Okay, so here's your formula for t-test. What you're doing, as you see here, x1 and x2, with that bar over them means average. So we have the means for each group. So the mean of one group minus the mean of the other, divided by the square root of the variance of the first group divided by the number of people in it, plus the variance of the second group divided by its number of people. Okay, so again, you can do all that math, but again, you don't have to. This formula gives us a p-value, and that's all we care about. So the key for you to know is you do a t-test to decide if your information is statistically significant, meaning it's not due to chance, or if it is due to chance. You're going to find that out, okay? So if you go through all that and you get the answer to your t-test, which is called a p-value, I don't know why they have to be different. It'd be nice if it's just the t-value. But if it's 0.05, well, decimal point 0.05 is the same as 5%. You just move the percentage place 2 places to the right, or the decimal place 2 places to the right to get the percentage. So if there's a 5% chance that it's dumb luck, then there's a 95% chance that it is due to the caffeine, or in this case, the independent variable. That's really what you want to know. And therefore, if it's 95% chance due to the independent variable, that's good enough for statistics, and you are statistically significant. If your p-value is higher than that, then you can't say you have 95% confidence that your independent variable is what caused a change, and you gotta find that confounding variable. So if you have a p-value of 0.039, move your decimal place 2 to the right, 1, 2, you have 3.9% chance that your reaction is due to dumb luck or just chance, but you have a 96.1% chance or a percentage of confidence that it is in fact due to the independent variable, which again is caffeine in this case. And here we go again. So again, the key to know, confidence level. That's what it's all about. I don't know what this link's about. It's probably not that important. Oh, there you go. It's telling you about confidence levels and the number of people you need in a population, in a sample, in order to get a confidence level that you're looking for. Well, that's good. It's handy to have that going into it. So here we go. Different studies have done different tests on global warming, and here they have a 95% confidence level that they're looking for there. All right, that's about it for this video. I think that took about 6 hours. Hopefully that worked for you, and I hope it's helpful. Take care. Let me know if you got any questions.